Alrighty, so I don't have that much time left, so maybe we're gonna do something fun. One of the things I have in here, so here is a super sampling, which is like anti-aliasing, which I kind of implemented, right? So, but I need to implement it for different things, right? So let's put a to-do in here, maybe AA for triangle, and also AA for line, AA for line. For rectangle, I'm pretty sure for the rectangle, we don't really need any anti-aliasing, right? I don't think it makes much sense. So, and here I have a 3D triangles. 3D triangles include like implementing a lot of rather complicated things, right? Because one of the things I wanted to implement here as well is Z buffering, right? So because I want to be able to render triangles that intersect each other, right? So, and maybe also do a little bit of a Z fighting, right? So I think I'm not going to implement specifically 3D triangles, but we can try to implement maybe circles that are floating in 3D. Let's try to do a little bit of a CPU 3D without any OpenGL or anything like that. I think it's going to be interesting. Right, so how do you do 3D at all, right? So, because I know that you can just like use one of the engines or one of the libraries, or even in OpenGL, you basically get the 3D automatically, right? But the question is, how is it even implemented, right? How do you implement 3D? So the problem of implementing 3D is essentially you have some points in a 3D space, right? So we have some stuff in the 3D space. Let's actually draw a cube. It's a pretty scuffed cube, but you get the point, right? Hopefully you get the point. So this is my cube, right? And you have some sort of a screen, right? You have some sort of screen and you have an observer, yourself, right? And what you need to do, you need to basically take all of these points and project them on the screen, right? So that's what you need to do. You need to project them on the screen like that, because this is basically how vision works, right? You have your eye, here's the eye, here's the screen, and you need to imagine that this 3D scene is behind the screen. It is behind the screen, right? And then we take the points in 3D space, and what we need to do, we need to somehow project them onto the screen in this sort of like a shape cone, right? So, and that's basically the problem that we're solving. So what we have in here is essentially the distance from the eye. So this is the eye, and this is the screen. Let's actually put like a screen. And this is an object, right? So this is the object. And you also have some sort of a distance from your eye to the screen, right? So distance D. So you have a point, and you need to find point prime, which is the point on the screen. We can maybe denote some of the coordinates, right? So this is the Z coordinate, right? So we're looking at the whole thing from the side, right? We're looking at the whole thing from the side. So that means here comes the Z axis, and up in this particular sort of view is going to be y-axis. So an x, from this point of view, goes like deep. It goes deep, so it's not really that important. So maybe I'm gonna even like put it like that. There we go. So maybe, just maybe, we're gonna say that the screen is located at Z0, right? It's located at Z0. And the eye should be located at somewhere like -1. So the location of the eye, let's actually denote all of these like things. Eye, let's say that it's going to be located at 0, 0, right? So it's located at the center, X and Y. And in terms of Z, it's supposed to be located at -D. Right, so it's located at -D. So this is what we have. Screen, in terms of like the center of the screen in here should be located at 0, 0, 0. P has coordinates, I don't know, let's actually call them px, py, pz. Right, so this is that. And what's interesting about p prime is that it's a two-dimensional one, right, because it's on the screen. Py prime. Right, how can we find all of this? Let's actually find only y of that projected point. Right, only y of that projected point, which will make it a little bit easier because that means we have to work only with py, pz point. Right, so we sort of like project this entire thing and we don't have to think about like anything else in here. So we have this line in here, right? We have this line, and we already talked about the formulas of the line, right? And how you can use it to actually find arbitrary point on the line, right? So let me actually maybe erase this entire thing. So we're gonna erase this entire thing. Cool. Let me see. So the formula of the line, the equation of the line is that y is equal to some k multiplied by x plus c. And essentially what you need to do, you need to find k and c. And if you have 2 points, right, if you have 2 points, you can find k as y2 minus y1 divided by x2 minus x1. And a c can be found as, I think it's like x1 minus k y1, if I'm not mistaken. So I do have this formula in the library itself when I draw the line. Right, when I draw the line. Where's... Oh, it's just like a line, okay. So yeah, c is basically k, yeah, so, but it's actually y. Yeah, okay. I could actually maybe reinvent this formula again, but I already reinvented it so many times, like I'm too lazy to do that. Okay, so we have something like this, right? So what I want to do, effectively, is to find k and c for this specific line between the I and p, right? So what that means that x1 is going to be equal to, well, I mean, we're actually doing that for yz. Right, we're doing that for yz. That means we have to replace x with z. Right, because in our case, as you can see, z acts like x. Right, z acts like x. So let's actually go ahead and maybe replace that stuff in here. So this is going to be that, and this is going to be z, z2, z1, and z1. Okay, cool. So, in our case, z1, the first point is going to be the I, right? And that means it's going to be minus d. This is the z of this thing. y1 is going to be 0. z2 is p, the z of the p, and y2 is py, right? So let's try to find the k for this thing, right? So this is going to be y2, which is py minus 0, right? So it's understandable. Then we're gonna have pz minus d, which is plus d in that case, right? So because we already have minus d in here. Okay, so this is that. And then y1 is going to be 0 minus k, right, minus k, minus 0, maybe I'm not going to write minus 0, pz plus d, multiplied by z1, right. All right, so that's cool. And then what we have to do, we have to take the z of p prime, right? And z for this thing is actually 0, right? So if we essentially put y to here. So it's going to be that is rather interesting. Okay, so I suppose I confused myself. What I was trying to come up with, I was trying to reinvent the formula where you have p prime x, px divided by pz. So this is what I was trying to end up with, but I actually kind of failed to do that. Maybe because I'm already tired. So yeah. All right. Yeah, I was trying to come up with this formula, but I actually completely messed up. So let's actually try to code this formula, I suppose. Yeah, because you just need to follow the process, and yeah. This is, by the way, the reason why I started to develop Nook. This is like precisely the reason why I started to develop Nook, because I do understand how to like do this entire process, but I always mess up this process because I have to keep track of a lot of like many little things, right? This is something that I was talking about in the Nook streams, right? So like every time I'm trying to transform some formulas or stuff like that, I just like mess up something, like I just forget something, and I don't know what to do. Like, but at the same time, it's not like doesn't mean I do not understand what I'm doing. I do understand. It's just like technically, mechanically, it's kind of difficult for me, right? So what I was trying to do, I was trying to get this idea and then come up to this thing, but I messed it up, right? And I'm not sure, maybe I should have just used Nook in this particular case. And the Nook thingy that I was talking about is this one, if you're interested in this thing, right? Yeah. So I'm gonna put it in here. Wati, thank you so much for Twitch Prime subscription. Thank you. Right. So, and essentially the idea is that if you have the point in 3D space, you just take x and divide it by z and y divided by z, and you get the point on the screen effectively, right? So there are some parameters depending on like how distant your eye is from the screen and stuff like that, and from that you can compute you know, point of view and everything, but you have to come up to that like this mechanical mathematical process. And I suppose this is one of the reasons why people are so scared of the math as well, because they think that it also requires like doing this thing which is super easy to fail. So yeah, let's go ahead and try to maybe do that, right? So you know what I'm gonna do? I want to take my code. I want to take my code of the triangle, right? So here I have a triangle. Here's the triangle. And this particular triangle example is actually rather cool because it's sort of like a boilerplate for like anything animational graphical with this library, right? So essentially I can just go ahead and copy paste this triangle in here, right? Let me do 3D, right? So I'm going to do 3D, and maybe I'm going to go ahead and just like remove everything related to triangle. So rotating point, I didn't think we're going to be rotating point. If I'm going to be rotating point, I can re-implement that. Right, I'm going to remove the triangle, I'm going to remove the circle, and there you go. So I have something, right? So let me go ahead and just compile this thing. Clang o 3d.c, right? So let me see. Conflicting type names. What is it conflicting with? Oh, okay. So I see I have some stuff that I have not committed yet. I'll have to remove that. Revert the buffer. Why are you forcing me to do all of that stuff? Okay, cool. Where is 3D? Okay, so let's try to compile it one more time. Okay, so it doesn't have a main because it's behind this macro, right? It is behind this macro. So let's try to define this macro. SDL platform .c. There we go. Right, and as you can see, we use functions that are not available, so let's actually link with SDL2 and maybe also with the math library. There we go. And if I try to run this entire thing, so we basically have nothing. Right, but now I can just go to the render. I can go to the render and do Olive.c circle OC, and let's just try to render a circle at the center somewhere, right? With a radius maybe 16, I don't know, and let's make it red, right? Something like this. So it's going to be red in 3D. There we go. Okay, cool. So this is a red circle. Of course, like maybe it would be nice to actually do something like 2020. Right, so it's a little bit nicer red color. It's still bright, but it's a little bit nicer, if you know what I mean. Right, it's a tiny bit nicer. Right. So let's maybe generate like maybe like a cube of circles, if you know what I mean. Right, so some sort of a cube of circles, but we'll need to know what's the dimensions of that cube, if you know what I mean. What are the dimensions of that cube? Let me create some sort of a thing in here. So maybe grid size. We get a rate from RPRTR. Thank you so much. Grid size, let's say, is going to be like around 10, right? So this is like a grid size. But then, what's going to be the padding between the circles, right? So let me think. Maybe grid pad. Let's say it's going to be 10, right? I think I want to call it grid count, right? Because it's kind of a discrete thing. Because then I want to know what's going to be the the size of a single like edge. Right. So this is going to be grid size, and if we do grid count multiplied by the padding, we kind of get the size in pixels of this grid, but not really, because we have to do -1. You know why? Right, because the amount of like paddings is always count -1. You have 3 points, and how many paddings do you have between 3 points? You always have 2. And you have 4 points, you have 3 paddings, so it's basically grid count -1 multiplied by paddings, and the amount of paddings is the size that you have. Right, that makes sense, I guess. Alright, so let's try to render all of that stuff, right? So let's actually try to render that in 2D. We're gonna start with the rows, so it's gonna be grid count plus y. And then we're going to start with x, right? So we have x and y in here. So this is x and y. And what we need to do, we need to render the circle. It should start from half of the width minus grid size divided by 2, right? Something like this, divided by 2. And then we have to do plus x multiplied by grid pad, right? So something like that. Maybe I should probably have like a different names for these things. So then I can use y as a separate variable. Well, I mean, this has to be x, right? So this is going to be x, but this one is going to be columns effectively. Right, so this is the column, and this is the column, right? And then we have y, height, row. And here we have x and y, right? So that's what I mean. So essentially that will generate a grid of the circles. And it kind of did, right? But what we're supposed to have in here is half of the grid size, not count. Right. Grid size and not count. Alright, so, but we can see the square because the radius of the circles is too big, or maybe the padding is not big enough, right? Alright, so this is the grid, and we have actually too much of a padding, I would say. So let's actually make like 50. Right, so this is the grid we have. Alrighty, that's pretty cool. So maybe I'm going to put the radius here to the constants as well. Circle Circle radius. Circle radius. Define circle radius. Maybe 10. I want to make it a little bit smaller. Right, so we already have a circle radius. Why didn't you tell? Well, I mean, it literally told me. I also have this color, so maybe I should use it as a color. Yeah, maybe I should. Let me move. No, I can't move them because the pixels are defined here. I mean, I can move that with the pixels. Who said I can't do that? I can just move all of that stuff with the pixels because I want to have my implementation alone with my constants. Right, so there you go. And so the circle, I think I want to use this color for the circle. I think it's a pretty nice color for the circle. Right, circle color. Circle color. So this is row and column, and interestingly enough, I still would like to call this X and Y, right, because it would make sense, because then I could make it a 3D. I could make it a 3D by throwing like another thing in here, by throwing Z in here, but unfortunately I can't easily do that. Right. So because of that, maybe I'm gonna call it like R, so sort of like a real. This is like the, yeah, we can actually call it C, which stands for cell, right? Because we're like doing that for a specific cell, right? For a specific cell, and this one becomes just that. So this is CX, and CY. All right, cool. So now, as I already said, we can try to make it 3D by introducing Z-axis. Right. So let's try to see if we can easily do that. And what's going to be the value of Z? Interestingly enough, what I'm thinking is that maybe we should normalize this entire shit in the screen as well. You know what I mean? You know what I mean? Yeah. I think we normalize that. It's going to be easy because, for example, in OpenGL there is normalized device coordinates, right? There are normalized device coordinates, and they go from -1, 1, -1, 1, -1, 1. So we have basically a cube 2 by 2 by 2 by 2, and essentially you render everything within that cube. And so the screen, if I remember correctly, is assumed to be at 0. Right, so everything in Z positive is considered to be like visible, right? Or something like that. I think it doesn't even matter which one you consider visible or not. So yeah, I don't think it matters that much. So because of that, maybe we're gonna be actually doing all of that in the normalized device coordinates. Yeah, I think we can try to do that in normalized device coordinates. And because of that, I'm gonna say that, okay, I'm gonna take 1 and divide it by grid count. Right. So this is gonna be the padding. This is gonna be the padding. So in here, width is basically 1, right? Not really 1, but it's actually 2. But not really. Right. So I can just take the grid size, divided by 2, and take like a negative part of it. Alright, so that would make sense. So grid size minus grid size. And since it's a minus, maybe I can actually swap these things somehow, like so. It's a little bit cold in here, so let me actually quickly close the windows. Freaking Siberia. Isn't it already fall? Yes, it's a fall in Siberia. What's the temperature in Siberia? Just a second. Weather Novosibirsk. The bot is dead. Oh, okay, it's a +10, but it's night actually, so it's a nighttime right now. So maybe tomorrow is gonna be more warm, probably. So okay, so in our case Z, we're gonna put Z. Let's render it at like half, right? And it probably doesn't really matter right now, so I'm gonna just like, you know, ignore it for now. I just want to translate everything to normalized device coordinates. Okay, right. Once we figure out X, right? Once we figured out X, which is by the way floating point in here. So all of that stuff is a floating point. And now what we want to do, right? We want to multiply them by the actual width and height of the sort of screen. So let me do it like that. So this is going to be the float, and then I can take X. X is supposed to be from -1 to 1, right? It's from -1 to 1, and essentially I want to translate it to 0, 1, right? So if I have something like -1 to 1, I can add 1 to it, effectively translate it to 0, 2, and then divide it by 2. And that way I have a value from 0 to 1. And then I can multiply it by the width, and that will give me a value from 0 to width. Right, so, and that's effectively what I want to do in here. +1 and divided by 2 multiplied by height. Right, so that's what we have. Cool. So, and all of that will effectively depend on the screen size. So yeah, it actually kind of repeats the aspect ratio of the screen, but maybe that's fine for now, right? So we don't really care about it too much. Okay, so let's try to introduce the z-axis, right? Let's try to introduce the z-axis. And this one actually is divided by 1, right? I'm not sure if that's a particularly good idea, but we'll see. Int c z 0, z less than grid count, plus z, right? So, and here we have a float, and z is probably gonna start at some sort of a padding. So let's actually establish that it's going to be after the screen at 0, 0, maybe 1, plus cz multiplied by grid pad. There we go. So it's multiplied by grid pad. So it's going to go in like from us. So it's going from us. All right. So the next thing we want to do, we want to project this point in 3D space to our screen. We can do that by dividing it by z, right? And we have to be careful to make sure that z is not equal to 0. Otherwise, we divide it by 0. And what's interesting is that if the z equal to 0, that effectively means that the point is right in our eye. That's why division by 0 is not defined, right? So because you can lose your eye, right? If you divide by 0, you instantly lose your eye because you have something in your eye. Right at the position of 0. Right. So, and after that, we can try to essentially render that point like so. So that should be fine, I think. So it didn't work properly, so let me put a CZ in here. All right, I wonder if it's gonna work. And that is not bad. Does it look like something 3D though? Which is rather interesting. So what if I say basically use 1 in here? Let's actually start with 1, right? So what is the first thing in here? We can't see shit in this mist. That's actually really surprising. What if I have 2 of them? We have like 2 of them. So I have a feeling that, oh, I know what's going on. I think it's too close to us and that's why we can't see shit. What if we start from half? Right, and let's actually render one thing in here. We start, okay, and we can see all of them. So there's supposed to be 10 of them. 3, 3, 3, 1. You know how I count things usually? For some reason, my brain likes to count things by 3. Right. So 3 is such a simple number that you can actually recognize 3 objects without counting them. Have you noticed that, by the way? At least my brain, right? So if I see 3 objects, I never have to count them because 3 objects are instantly recognized as 3 objects, right? So, and what I usually count is I count the groups of 3 objects. And because of that, like I have 3 groups of 3 objects. I know this is 9, and then I have 1. Use 3 or 5. For some reason, my brain is incapable of recognizing 5 as a single object. I always recognize 5 as 1, 3, and 1, 2. Right. So I have to do that additional logical step usually. Okay, so at half of the way, we can see the entire thing, which makes me think, what if we take the padding as 0.5 and divide it by the amount of things, right? And that's going to be our padding, right? So I'm going to just start with that. Can we see shed? Okay, so we can see shed in here. So what if I have 2 of those things? Right. So we can actually go deeper. So we can try to do another layer in here. You see where I'm going with all of that? You see where I'm, like, it's actually starting to look like 3D. I'm not using OpenGL or anything like that, so that's quite important to remember. I'm not even using OpenGL or anything. All right. Okay, so I just like made it even smaller, and we can actually try to use like the full thing in here, like a grid count. All right, and this is more or less like a full cube. But the problem with this full cube is that you can't see that it's actually 3D. You need to make it move or rotate to actually feel its 3D-ness. Is that even a word? I don't know. I don't speak English. So we can also make it like maybe smaller, maybe like 5 by 5, right? So yeah, so that's like looks a little bit better. But you cannot tell, is that 3D or is it just like the points that go from the center, right? You can't see 3D unless it's spinning. So let's actually try to rotate it, maybe. So we're gonna be rotating it maybe around the y-axis, right? Let's try to rotate it around y-axis. So, okay. But the question is how... That means we have to rotate y and z, right? We need to rotate y and z. So, and we need to figure out what is the center of rotation. So let's say I already taken C... God fucking damn it. Okay. I want you to use CY as the center and CZ, but they're already taken. God damn. Okay, so maybe I should rename that. So let's rename CX to something else. What should I call it? So it's more of an index. Maybe we can call it IX, right? So it's just like an index. The same goes in here, right? IY. And this is. Okay. So in terms of like Y, the center is located at 0, right? So this is no doubt. Then the center for Z, the entire thing Z starts at half. So maybe we want to move this somewhere, right? Z start, right? 0, 5 and 0, 5 Z start. There we go. So we start somewhere here, and then what we want to do, we want to take the grid size and divide it by 2, right? Because we're going like deep into this thing, and the center of this thing is going to be somewhere there. So this is effectively, the center. Okay, so let's say, so this is Z. No, if we are rotating around the y-axis, that means we have to use cx and cz. Yeah, so we have the x and z. Okay, so it doesn't really matter. So it's going to be the same for cx. It's also 0. So let's actually say that z is going to act like y, right? So in our case, x plays the role of x, right? So x plays the role of x, and z plays the role of y. Okay, so let's actually find the distance between them. So it's going to be dx. We take x minus cx and z minus z. Okay, that's cool. So now what I want to do, I want to find the angle of this thing. So the angle is going to be a tan 2 dz dx, and I put z first because z in that case acts like y coordinate, right? So it plays the role of the y coordinate, right? So then we want to find magnitude, and magnitude is essentially square root of f dz dz. Let's start with dx plus dz dz, and there we go. We have a magnitude. So this is the angle, but we have to constantly update that angle, right? So we have to keep track of maybe some sort of a global angle, which starts at 0, and every time we update, we take the next frame, we do angle plus 2 pi multiplied by dt. So we have like a 1 round per second. Yeah, that sounds fine, right? So it's basically the same speed as rotating the triangle that we had. Okay, cool. So now what I can do in here, so I can say that, so this is our angle in here, but I need to call it something different, right? So this is the angle of the vector in here. So let's call it like a and m, whatever. Right, and then I want to convert everything back, right? So how do I convert everything back? I do dx equal to so x is cosine a plus angle, right? So a plus angle multiplied by m. So this is dz a plus this one is going to be sine, right? This is going to be m. Okay, so we've got rotated dx and dz, which we have to convert back to x and y. Right, we have to convert them back to x and y. So that means we have to add them. So x is going to be dx plus cx, and y is going to be, z is going to be dz plus cz, right? So we're basically converted everything back, and then we project the entire thing to the screen, and then we render that on the screen. All right, so that's how we're going to be rotating. So I know that you can use like the matrix for rotating this entire thing, but I'm too lazy to come up with the matrix. So A10, well, I mean, it's already rotating. God damn, it's rotating fast. So yeah, isn't it cool? I think it's pretty cool. So I think we have to have like a even amount of numbers, so we don't have that weird how to say, weird axis, right? So, and maybe it has to be slightly slower. So, and also A10 too, it has to be F, right? And it's too fast, so okay, so let's actually do something like this. It's the other way around. Yeah, boy, it has to be even slower. And furthermore, I have to use the F thingy for both cosine and sine. So that should be for, oh my god. Look at that mother flipper. Look at that mother flipper. Isn't that freaking cool, mate? All without OpenGL. Yeah, isn't that cool? Isn't that cool? I think it's pretty cool. So, so what about like 25? I want to make it even smaller. Yeah, boy, 3D without OpenGL. This is how OpenGL is like basically works, right? Why do you use Clang instead of GC? I just implemented like a 3D graphics from scratch without OpenGL, and the choice between two compilers is the only thing you're interested in right now? Seriously? Is that the only interesting thing you have on the screen right now, or is it just... What? Come on, don't disappoint me. Do not disappoint me. Okay, and you know what's interesting is that we can actually try to... We can try to compile that to WebAssembly. And we can try to... can you make it bigger, cover an entire canvas? Well, I mean, cover an entire canvas, basically the question of making it closer. Right, so let's actually put like a 25. Right. Yeah. We can also make the resolution a bit bigger. So let's actually do 16:9 multiplied by a factor. It's just like, I don't know. I feel like I can find a cure for cancer in front of everyone, and there will be always one guy who will ask something like, but why did you do that in Emacs instead of Vim? Like, why does it matter? Why does it matter? Why people care about such a trivial, not important things? Why? It's just like, like I'm trying to do cool shit, and people just ask about these trivial, not important things. Like, why? I don't understand. It just like makes me sad. It just like makes me sad. You know what I mean? Okay, so let's try to maybe compile that to... I'm sorry, like I'm not attacking any one person or anything like that. I'm just saying that this kind of question just makes me a little bit upset. I'm just saying, right? So I'm not saying that the argument of like choosing the compilers is like invalid or anything. It does matter, but in the context, in this specific context, like it's... Why does it even matter? Why does it even matter? I don't know. Anyway, I'm sorry, should calm down. Let's try to build that as a thing. So I think I'm gonna actually put that stuff into examples. And now I feel like an asshole. Like, I don't know. It's just like... No, I'm not trying to be mean or anything like that. I'm just like saying my actual feeling, and now I feel like an asshole, right? So I guess I am an asshole. I guess I just have to accept that I'm a freaking asshole, right? People are just genuinely asking important questions, and I'm just being mean to them and being an asshole. And there's nothing I can do about that. I guess I'm just like naturally an asshole person. Anyway, so let's continue. It's just like, yeah. Keep in mind that I'm an asshole every time you ask a question. There's nothing I can do about it. Maybe I was born an asshole. Yep. Born through an asshole. Anyway, okay, so this thing does not work because why? File not found. That's very strange. Oh, because I never actually compiled anything. Alright, this shit works in the browser. So it's also not perfect cube, right? Because we're pretty much dependent on aspect ratio. But yeah, this thing works in the browser as well. It's pretty cool. And the fact that we're rendering that pixel by pixel is actually also pretty cool. Why not Firefox? Yeah, that's a good question. Thank you for asking. It's like, it's all cool and all, but Zozin, why did you paint them red? Do you hate blue? Please explain yourself. Hmm? Oh, you implemented 3D without OpenGL? Fuck that. Why did you use red? Why did you use red? Why didn't you use blue? You hate blue. You're a blue hater. Anyway. Okay. Gosh, I'm such an asshole. I just can't help myself. Why am I such an asshole? Right, so... Dark Might 10, thank you so much for Twitch Prime. Does anyone have any questions? I think we already went over like 2 hours, and we have like so many people watching this. Okay, so why do you all watch an asshole ranting about shit? I have a question. Why? Okay. Are you happy now? Are you happy? Okay, let's actually maybe make it, I don't know. Can we make it rainbowish? If you know what I mean? How can we make it rainbowish? So essentially, we can try to split the whole space in 3 points. And then we can interpolate between like 3 points. It's too much work. I don't want to do it right now. Let's put it this way. You inserted 2 circle colors. Right, so, and let me just put this thing in here. So this one is going to be red. FF20. Boom. It's gonna be FF2020. So how easy would it be to make a function that spins whatever drawing you throw in it? So we need to have at least support for textures, and we need like a mechanism that can map texture in 3D space. That's actually a lot of work. It's pretty hard right now, but it's not impossible if we just like put some effort into that. But it's not like a single stream, it's like maybe 2-3 streams. Right, so we have to implement a lot of things in here. Okay, so for the color, I'm gonna just do circle colors. Let's actually put the color in here. uint32 color, what is that? IZ divided by circle colors count. Alright, circle colors count. Okay, so this one is going to be essentially size of circle colors divided by size of circle colors. Okay, alright, so let's try to recompile this entire thing. Boy, boom. So yeah. Every color for everyone. I mean, we probably have to do also the combinations of colors, right? So like a yellow, cyan, magenta, and stuff like that. Let me actually see. Maybe we can do that. So let me see. Okay, so the next thing is gonna be like pairs. So this is gonna be FF, then FF20, and then maybe 20, like so, right? Are we gonna have enough like layers to even do that? That's a good question. So yeah, so we have like 6 of them. So we already, well, yeah, we're already used to them. So there's like 6. Let's actually make 10. Right, so they're supposed to like circle, right? They're supposed to circle. So that's a mess. That's a fruit salad. Well, yeah. And also they are not rendered according to their z-axis, so it's kind of like anyway. It's a pretty dang shit, not gonna lie. It's a pretty dang shit. I've got an idea, chat. Let's actually do something like ix plus iy plus iz. Oh, this is a mess. Okay. All right. I've got an idea actually. So let me try to do that. We can, yeah, so we can do yx, and we can divide it by the grid count, right? So we can divide all of that by the grid count, so this is going to be float, and this is going to be float. And then I can multiply by 255, but effectively what I can do is just multiply this by 255 and then just divide it by this, and I've got what I need to do. So this one is going to be red. Let's assign this to red, then G, and then B, or in this case, this one is going to be Z. And let's construct a color out of those mother flippers, right? So this is going to be alpha 0, 0, 0, 0. Okay, so we're gonna do that. Red is first, as far as I know, is just like 0 bytes, right? This is 0 bytes, and then this one is gonna be G, and this one is gonna be B. So G is 1 byte, this one is 2 bytes, right? And this one is 3 bytes. Okay, so then essentially, so does it compile? I think it compiles, and let's actually, holy shit, that's so cool. It's basically RGB space, right? So somewhere at the angle we have black, and the other angle, I'm sorry, in Russian language, corner and angle are the same words. So like literally we use the same word for a notion of angle and corner. So in one corner you have black, and in another corner you have white. Essentially what I can do right now, I can remove everything and leave only the corners. I use the right word. I can use only the corners, and then I can basically connect them with triangles. We already know how to draw triangles, and I will have an actual 3D effectively, right? But what's interesting is that I won't be able to implement Z-buffer. So, and what I'm thinking is that, how would I implement Z-buffer? I would have to do an opposite operation of projecting the triangle to the screen, right? So let me show you. So I have a screen, I have the eye, and I have the triangle, right? So this is a 3D space triangle, right? Here's an eye, and I projected the triangle on the screen somehow, right? So I've got 3 points, and there we go. So this is 3 points, and then I draw the triangle on the screen as usual. But then I want to figure out the z-axis of each individual pixel of that triangle, right? So for instance, I'm drawing this pixel of the triangle, right? What is the z value of that pixel? What I'll have to do, I'll have to project that pixel back on the triangle, right? So I'll have to take the eye, I have to like draw a line from the eye and through that specific pixel back to the triangle, and only then I'll know the z value, and that way I can fill up the z buffer, and then I can use the z buffer to actually cut out the you know, different triangles and stuff like that. And this is rather hard, right? So essentially you have 3D line, right? 3D line, and then you have a 3D plane, right? 3D plane. And you need to find the point of intersection of 3D line and 3D plane. Oh, okay, it's not that hard for you math students and stuff like that, but I'm this kind of person that doesn't understand shit unless I can like reinvent it. Right, for instance, I use this formula and I managed to reinvent it once, so I kind of understand it, but at the same time I couldn't reproduce that, so I don't understand it. But anyway, so for me it's kind of important to sort of like reinvent this entire process, so that's why I consider that hard. So yeah, that's basically my thoughts about the Z-buffer. Anyway, so that's it for me. Thanks everyone who's watching right now. I really appreciate it. Can you just use interpolation from the z coordinate of the corner? So I could use that, but the projection actually screws everything up. So the projection is not linear. That's the problem. You just can't do that linearly. I don't think so. You can interpolate 1 over z. What? That's actually a pretty cool idea. Nifty wifty. Wait. That kind of makes sense. I'll need to think about that. Thank you. Because that also makes sense. It is actually easier. Ooh. The projection destroys information. Yeah, that's true. If you interpolate my 1 over z. Okay, thank you so much. I'll think about that. All right, so thanks everyone for watching. Maybe we should rate somebody, right? So because we were rated by people, so we have to give back to the community. Yeah. Learning math through programming is actually super fun because it's visual. You can actually see. So George Hot's actually streaming, but we're not gonna raid him because he already has shit ton of viewers, so fuck that. He should raid us instead, right? So the bigger streamers have to help smaller ones. It is not correct to, for a smaller streamer to raid a bigger one. Okay, let me see. I wanna raid somebody who's a smaller streamer, right, so... Super slow. So, do we have anyone who's developing... Compiling is dead. I really like this title. And they're programming in Java. They're doing game dev in Java. Reverse engineering. Reverse engineering actually sounds interesting. Is this really reverse engineering? Doesn't look like reverse engineering, I'm sorry. Twitch! Why is it so bad? Oh my god. It's unbearable. This is the most unbearable website I've ever... Okay, so maybe I'm gonna actually rate Hero Dev because he's doing C++, which is rather close to what we're doing. Well, that's real. So far, I've seen some MS Paint. I'm sorry. So I know nothing about this streamer, and this was my first impression. So I'm sorry about that. Come on. All right. So I started the raid. Hopefully. The interface hasn't updated on me yet, so... Oh, okay, so it's updated. Cool. Alright. So that's it for today. Thanks everyone, and I love you all. Get ready for the raid. Get ready for the raid.